Hello everyone, this is Nikita. Welcome to the episode 64 of Microsoft Hour of Code brought to you by Millionlights. Millionlights is a TV channel dedicated to improving skills of people and their employability. Now, let me tell you more about Microsoft Hour of Code. Microsoft Hour of Code is a series of lectures, courses and talks by experts who are going to discuss the latest Microsoft technologies, topic related to programming and industry forecast that are all focused on employability. As you know, we are learning developing Microsoft SQL Server Databases. This course is basically for people pursuing computer science. This content has been created by our partner Microsoft, and today we have Malcom and Bolton from Microsoft with us. Our expert will take you through tables, indexes, stored procedures, and other database objects. Learn about techniques from designing indexes, managing transactions, and optimizing performance and concurrency, and get best tips and practices. These courses can help you earn at least 4 lakhs a year, and for those who are already working, experience strongly influences pay in this job. So you can definitely get an increment in your salary. Now, let's move towards the course. Developing Microsoft SQL Server Databases. The topic we covered in the previous episodes are implementing tables and views, implementing indexes, and implementing stored procedures and functions. In this episode, we will start new topic, managing transactions, implementing in-memory objects. So, let's get started with the managing transactions.
Welcome back. So far we've looked at tables, we've looked at indexes, and in Module 3 we looked at stored procedures and functions. What we're going to look at now, having taken a little time to learn a little bit about how we can encapsulate programming logic in functions and stored procedures, we want to kind of take that to the next level and talk a little bit about how we can use that programming logic to manage transactions and make sure that our data, our modifications to the data is done in a kind of atomic and secure fashion that makes sure all the changes go through. So to talk more about that, Christian is with me again. So Christian, what are we going to cover in this one?
Great, thanks Graeme. So first of all, we're going to start off by defining what a transaction is and how we manage and use transactions, because it's really a fundamental concept for how we use SQL Server. Then we're going to have a look at understanding isolation levels, and again this is another core topic, certainly for your use as you develop against SQL Server, but definitely in the exam there'll be lots and lots of questions and scenarios that will really lean on your understanding of different isolation levels and what that means. Then we're going to have a look at locking. We're going to have a look at how and why SQL Server uses locking. And then finally, we'll have a look at some locking problem scenarios and discuss what you can do and how you can really troubleshoot that.
All right, sounds good.
So let's start off. So managing transactions. So defining a transaction first. So a transaction is a group of tasks that defines a unit of work. I guess it doesn't really have to be a group of tasks, but the key point here is that it's a unit of work that either must succeed or fail together. So no partial completion is permitted. So individual data modification statements are automatically treated as standalone transactions, and we call these implicit transactions. So if you did a single update statement, that's an implicit transaction in there where it will either succeed or fail. It won't partially complete.
So if I were updating all of the rows in a table where the value was something, it wouldn't get halfway through and update some of them but leave the rest of them as they were. Either they all get updated or
exactly. And you don't need to make it explicit that it's a transaction because it's implicit in what you're trying to do there.
Okay.
And then we have explicit transactions. So you can also control this to define your own transactions. So we can use begin to begin a transaction, commit to finish the transaction and say, I've definitely finished and I want to commit all those changes. Or you might want to say, actually, there were some errors detected there, so I want to roll back those changes as well. And we call those explicit transactions. So implicit and explicit transactions.
Okay. So we've got an example on this slide then of implicit examples. You want to talk us through this?
Yeah, sure. So we've got partial success here, even with its structured exception handling, because this isn't a transaction. So even though we're saying insert into the orders table, insert into the order details table, and if there's an error, send me, raise a flag and send an error number. What we're not saying is, I want you to roll back those changes. So if we had an insert into the order details table that failed, we wouldn't roll back any changes that we'd inserted into the orders table.
So there's actually two transactions going on here. There's two implicit transactions. There's an insert into the sales.orders table where either all of those inserts into that table succeed or they all fail.
Exactly.
But then regardless of whether, well, presumably if they succeed, we then go into the next step and we start to insert order details, and either that all succeeds or fails. But if that fails, it won't roll back the inserts we've already done into the orders table.
Exactly.
Okay.
So then we move into explicitly defining a transaction. So we take that same piece of code and we wrap it in a begin and commit transaction. And because we have this try catch, what we're saying is if an order fails, so that one of these insert fails, then we're going to roll back that transaction. So I want to insert an order with order details or neither.
Right, so in that case, I don't end up with kind of orphaned orders that don't have any matching details. Yeah. We roll the whole thing back if anything goes wrong.
Exactly.
Okay.
Should we have a quick look at that?
Let's look at that.
Okay, so we're going to switch over to use a database called T-SQL. I'll just clean up any of these tables. So we're going to create a table called simple orders, simple order details, just as we've seen in the example slides.
Okay.
So I'm going to execute this try catch to insert two orders with two sets of order details.
Okay.
And I've got a failure there. So I'm conflicted with a foreign key constraint. So we looked at primary keys and foreign key constraints earlier. So that's failed.
And you caught the catch section there, just because we haven't talked about structured exception before. The reason that hasn't shown up as a red error is because we actually caught the error and then handled it. So
yes, yeah,
you've got your own error handling logic there, yeah.
But if we then have a look at orders and order details, we've actually got a partial success. So we've got one order with order details, and we've got a set of order details with no, we've got an order without any order details. Yeah.
Okay. So clearly that's not what we want.
Exactly. So we'll clean up those tables and recreate them again.
And there's nothing different in the definitions of the
table.
Nothing up our sleeves. It's just the same table.
The same. What you see is what you get.
Okay.
So all we're doing now is wrapping a begin transaction and a commit transaction around here. Okay. And if they succeed, then everything will be inserted. Okay. But we've also got this catch here. So if there's an error, we'll roll back both of those changes.
Oh, okay.
So let's run that.
So that one's worked. We've inserted one order and the order detail that goes with it.
Exactly, yeah. So let's delete those rows and execute something with an error. So we've got the same error that we had before.
Caught the error, yeah.
But this time we've got no orders inserted.
So even although the order statement we know would have succeeded, the order detail statement failed, and therefore the whole thing was rolled back. So we don't end up with that orphaned order.
Exactly. And then let's just clean that up for later.
All right, great, thanks. So transactions then clearly a core part of maintaining. If you've got multiple tables and you're inserting into them and you want to maintain that integrity, it's really important to be able to do these with transactions. What if I've got multiple users accessing all of those tables at the same time, or multiple applications accessing? And we've got this concurrency issue. Talk to me a little bit about how I deal with that.
So exactly. So managing concurrency is the ability for multiple processes to access the same data at the same time. So we're talking about lots of users interacting with the same data at the same time. That's what we call concurrency. And there are really two approaches to managing this effectively. So pessimistic is this first approach. So that assumes that lots of different processes are going to try and read and write the same data simultaneously, and uses locks to prevent conflicts. And this is the default and is the kind of the traditional concurrency model for SQL Server, is to use locking based on pessimistic concurrency to remove access to avoid these kind of conflicts.
So I'm pessimistic. I'm assuming that you're going to try and update the table at the same time I'm updating it, or the row at the same time I'm updating it. So I'm going to prevent you from doing that.
Yeah, exactly. And the other approach is optimistic. So optimistic concurrency was introduced in SQL Server 2005. We've got a lot of really good stuff in SQL Server 2005. And optimistic concurrency introduced these snapshot-based isolation levels, which use row versioning rather than locking to manage concurrency. But pessimistic concurrency is the default, and in terms of your learning towards the exam, you need to be very, very familiar with this idea of this pessimistic concurrency approach and how locking works.
Okay, so as it says there, pessimistic is the default.
Yeah.
So what about some of the issues I might face if I'm having to deal with concurrency issues?
Yeah, so we've got a number of concurrency anomalies with lost updates, dirty reads, non-repeatable reads, and phantom rows being inserted. And these are really, we would decide whether or not these types of anomalies were attractive, so they may actually be useful to us, and we would use something called isolation levels to control whether or not we wanted these non-repeatable reads and dirty reads to be introduced into the application.
So can you talk me briefly through each of these things? What for example, is a non-repeatable read, for example?
So a non-repeatable read, for example, is if we had I wanted to, say I'm in a shop, just to give a physical example. So I'm in a shop, I'm closing down my shop, I'm going round all the tills, calculating how much each till has taken during the day. And I go to till 1, and that's taken a certain amount. I'll go to till 2, till 3, but the tills are still trading, and by the time I get back to till 1, that value is different. Right. So it's a non-repeatable read. So once I've read it, by the time I read it again, it may have changed.
So in the database world, if I've got two separate applications or users accessing a table, I might read one value and go off to do some additional work, but in the meantime, someone may update that row and change the value that I've originally read.
Yes,
it's a non-repeatable
exactly. And that may or may not be acceptable to you, and you can prevent non-repeatable reads, or you can enable repeatable reads for yourself by changing the isolation level, which will lower your concurrency, so you can keep people out of the data in order to maintain your repeatable read. Right. It may make more sense when we talk about the isolation levels.
Yeah, okay, excellent. Which we're about to do.
Yes, so isolation levels. So the first isolation levels. So we're going from very flexible in terms of concurrency, allowing everybody to access, right the way through to very, very restrictive. So starting off with read uncommitted. So what this means is I'm happy to read data that hasn't been committed. So what we sometimes refer to as dirty data. So if I'm selecting from a table, I want to get rows that may not exist or that may not be valid. So I may get an order details that doesn't have an order as yet, or something that gets rolled back.
Because there's another transaction that's only partially complete at this point.
Yeah. So the benefit of this, if you like, is that it doesn't hold locks when reading data. But the downside is that you're getting this uncommitted data.
Okay.
And the next one is read committed. So read committed is the default isolation for SQL Server. And basically that means that I'm only interested in data that has been committed. Okay. And the way that I will do that is when I'm reading data, I'll take a lock to prevent people updating it.
Okay.
While I'm reading it.
So it's going to allow non-repeatable reads and phantoms. I'm guessing in this instance, so the example would be if I've read the data and before I finish my transaction, another transaction might go in and modify something I've read, but I've already read it. It was committed at the time I read it.
Exactly.
So that's fine. And similarly, I might get all the rows from a table, all the committed rows at the time, but in between times, another transaction might come in and insert a row. So there's a phantom value that's in that table, but I'm not seeing it because I've got the committed values.
Yeah. So people will often use read uncommitted. Because it doesn't take locks to read data, there's this kind of expectation that it's more performant, which it is, but you're causing lots of problems in the fact that you're not locking data that you're reading. Whereas with read committed, what we're saying is if somebody is writing data, I'm going to wait for them to finish before I read it. So I could be blocked by somebody writing data.
Okay, that makes sense.
Makes sense.
Well, let's move on to the next one, which is repeatable read.
Yep, so repeatable read. So the difference between read committed and repeatable read essentially is under read committed, if we're reading from a table, we will take a shared lock, and we'll talk about locks coming up, in order to read that data, and then we'll drop that shared lock once we've read it. But under repeatable read, what we're saying is, I'm going to read that data, but when I read it again, it needs to not have changed. So I'm going to put a lock on it, and I'm going to hold that lock till I've finished what I'm doing.
So, and if there's another transaction that's ongoing, we avoid that situation with read committed, where I've read all the rows from a table. If I go back and read them again for whatever reason, and in between somebody has tried to insert, they won't have been able to insert because I'll have held a lock on the table.
Exactly. So there's benefits to that in terms of the level of isolation you have for yourself, but you sacrifice concurrency for that.
All right. Well, the next one on our list is serializable. So
yes.
Tell me a little bit about that.
So serializable is effectively, you're effectively saying everything I do, I want to lock everybody else out. So you're serializing access to the data. So it's a very, very restrictive in terms of the isolation that it provides. It makes your transaction very isolated, but it will block everybody out. So we tend not to use it very often in kind of day-to-day operations. We would really use read committed, repeatable read as something that's a bit more loose in how we can flexible in managing concurrency.
Okay, so I guess serializable is its place would be where there isn't a high likelihood of lots of different concurrent users trying to access the same data, because otherwise I'm just going to have locks that prevent anything getting done.
Yeah.
And I guess the important point at this stage, just to re-emphasize, when we talk about these locks, it's for the duration of the entire transaction, from the point when I first access that piece of data right till the transaction gets committed or rolled back, which is why we're talking about this having talked about transactions. Because while our implicit transactions, individual statements, will hold locks and then release them, by and large, unless we're talking about huge volumes of data, those are over fairly quickly.
Yeah.
But if I'm actually implementing an explicit transaction that does lots of different things, I might actually end up holding lots and lots of locks until I'm ready to commit. So the next one in our list then is snapshot isolation.
Yes, so Snapshot, as I said, is new for since 2005, and Snapshot is the only optimistic isolation we have. So as I mentioned before, it uses row versions rather than locks. So effectively, what happens is when you go to write something, the previous version of that row gets stored in the version store, which is in tempdb, and then if somebody wants to read that committed value, it will be returned from tempdb instead of them being blocked.
So we're not locking them out, we're allowing them access to the previously committed value.
Exactly.
And then when we're finished, our transaction will be committed, and that then becomes the committed value.
Exactly. So we would use snapshot isolation to help us resolve these situations of readers and writers blocking each other, because it allows for much greater concurrency in those kinds of scenarios.
Okay, that makes sense. So let's move on and look at locking. And we've talked about the isolation levels and the fact that they incur locking. I guess we probably need to drill down a little bit and understand how does that locking mechanism work. So let's take a look at that.
Sure. So in terms of understanding locking then, so SQL Server by default uses locks to deliver the level of isolation that you specify. So remember, we are read committed by default. So there are two main locking modes that you really need to be familiar with, and that's shared and exclusive, or SH and EX for short, as we'll have a look when we come to the demo.
Okay.
So whenever I read data, I need a shared lock in order to read that data. And a shared lock is compatible with other shared locks, so anybody can read the same data at the same time. So we've got a good concurrency.
Okay.
Now, whenever I want to write data, I need an exclusive lock, because we can't have multiple people writing the same data at the same time.
Okay.
So only one person will get this exclusive lock in order to update the data.
Right. Okay, that makes sense.
But the key point to this is that shared lock and exclusive lock aren't compatible. So if I want to read something that somebody's writing to, I will have to wait until they finish writing.
So if you've
And
already
same
got an
the other way
exclusive
around.
lock on it, you then can't get a shared lock. And if there's already a shared lock on it,
You
I
have
can't
to
get an
wait
exclusive
for that to drop in order to be able to do your write.
okay. So
Okay.
what about these other locking modes then? that we-
So there are a couple of other locking modes as well. So we use the update lock. Again, we'll see in the demo, and the main ones are shared and exclusive. So an update lock is taken when a process needs to read data before updating it, and it's involved. It's part of how SQL Server works to help us prevent deadlock. So it's automatic, and you wouldn't control this behavior. And we'll see an example of where it fits in. So if you wanted to do an update based on data that you read, you would take an update lock before taking an exclusive lock.
All right. Okay, I see.
Okay. And intent locks, so we would have an intent shared, intent exclusive, intent update lock, is basically used to indicate locks that are present at a lower level of granularity. So if I want to read a row, so I'm going to take a shared lock on the row, then I'm going to take an intent shared lock on the page, and I'm going to take an intent shared lock on the table. And that is to prevent somebody coming in and taking a higher level lock. It's like if I wanted to do, and somebody else is coming in and they want to take an exclusive lock on the table. So instead of SQL Server having to go down and see am I free further down to be able to lock this whole table, if there's an intent shared lock at that table level, it's an indicator that there's a lower level lock that's incompatible for the write.
So I've locked this row, so I'm reading it, but chances are I'm going to want to read more than this one row from the table, so I'm intending to lock the rest of the table. Gotcha.
Yeah.
So what are some of the problems we might hit with locking then?
So blocking locks is the most common kind of discussion point that we have around locking, and we've alluded to that a couple of times around shared locks and exclusive locks. And it's this scenario of I've got lots and lots of users reading catalogue data on a website. They're doing lots and lots of searches, but then I want to update something. These read locks are incompatible with exclusive, shared locks are incompatible with exclusive locks. So this combination of read-write activity is what causes these blocking locks. So to define a blocking lock, it's really that processes are waiting for access to resources. It's not wrong, it's how the product works, and whether or not that blocking lock is a problem for you depends on your business logic and your application in your scenario.
So I'm guessing you're building an application where you would have to have either some sort of timeout while you're waiting for the lock, or some sort of retry mechanism that says, well, if you can't access the table, wait for 30 seconds and try again, or whatever it might be.
Yeah, it's a very, very common performance tuning scenario where you have blocking locks, where you're developing on a small database, small data sets, the queries run really, really fast, so nothing's ever a problem. Suddenly you've got a massive data set, and the query that you wrote that was sub-second now takes 10, 20, 30 seconds to complete, but is holding locks during that period and is blocking other processes.
Right, makes sense.
So we do a lot of kind of troubleshooting around mature applications with varying data sets. Yeah.
So what about deadlocks then? Tell me about that.
So a deadlock is another interesting term, a bit like parameter sniffing. It sounds like
sounds really exciting.
It sounds like a cool term. So a deadlock is basically this principle of two processes each hold a lock that the other one needs to continue. So they're stuck in this deadly embrace of I can't complete because I need to get a lock on this resource, and you can't complete because you need to get on the lock of the resource that I have. And so we've got exactly the same requirements, just the other way around.
Just after you, no, after you, no, after you.
Yes, yeah, exactly. So and SQL Server will automatically detect and resolve this situation. Because if it didn't, then you'd just be permanently hung. It wouldn't go anywhere. So SQL Server will detect a deadlock, and it will automatically kill the transaction that is the cheapest to roll back.
Right. So there's less work involved in rolling back the transaction.
Exactly. So it may not be immediately apparent to you why it's chosen that specific one, but it's chosen it specifically because it's cheaper to roll back the changes that it had made.
And I'm guessing that the application whose transactions roll back then just receives an error, and if this is likely, it's one of the things you should be checking for.
So your application needs to be able to handle deadlocks and to reissue that transaction, right. and everything carries on. So deadlocks themselves aren't necessarily a problem, and lots of applications will infrequently see deadlock events, and as long as the application handles them appropriately, it's not a problem. It's when something changes and you start to get several deadlocks in a kind of frequent time period. Several deadlocks in a day, for example, would be something to investigate. One deadlock every 6 months may not necessarily be an issue for you.
And it might be. I've seen examples in the past where if you've got one stored procedure that updates the customers table and then the, addresses table in that order, it's probably not a good idea to have another stored procedure that does the same updates or updates to the same tables in the opposite order, because then you're increasing the likelihood that one connection will lock one table while the other one locks the other. So
exactly. So there's a development best practice there to do your table updates in the same order
of your stored
procedure application. Yeah, exactly.
So a couple of trace flags you've got listed here.
Yes, so a trace flag, we haven't mentioned trace flags up to now. So trace flags are a way to enable what were undocumented behaviors in SQL Server, but it's now we would use them to enable extra functionality in the product. And in this case, we've got a trace flag 1204 and 1222 will spit out lots of additional information about what's happened when a deadlock was detected. So what we would typically do is, if you know that you frequently get deadlocks, you'd probably enable these trace flags permanently, so you could analyze the outputs and work out and resolve these deadlocks. And how you would switch that on is by using DBCC trace on. So we've got in this example here 1222, which provides, this is the SQL Server 2005, I think this one was introduced, and it spits out an XML output of the blocking details, and 1204 was an older version of that. And sometimes we'll enable both, and certainly within the context of the exam, you should be aware that they're both deadlock-enabled trace flags. Okay,
and I can turn them on with DBCC trace on.
Yeah.
Are these trace flags I can also configure at the command line when I start the SQL Server service to it?
Yes, yeah, exactly. So if you go into Configuration Manager, you could add a startup parameter of -T and then the trace flag, and then it'll always
start
be there
whenever SQL Server comes up.
Yeah,
okay,
exactly.
Great. All right, so we're going to switch over to a demo, and we'll have a look at how we do this.
Okay, so the first thing we're going to do here is to set the transaction isolation level to repeatable read. So we talked about repeatable read isolation level as allowing you to read the same data twice. and that's different from the default, which is read committed. Shall I just run that? And then we're going to start a transaction. We're going to begin transaction just to select star from the employees table where last name equals Buck. And the reason that I've set it to repeatable read rather than leave it at the default is if I was on read committed, then I would take a shared lock on the row, and as soon as I'd read the data, I would drop that shared lock because it's a non-repeatable read. But because I'm now in a repeatable read isolation level, I'm holding that shared lock for the duration of the transaction. And because I haven't finished the transaction, I'm holding a shared lock, and we can go and have a look at those details.
Okay, and just to clarify, the transaction isolation level that you've set there is for this session. You haven't switched the database into a different mode, it's just for this session.
Yeah, exactly.
Yeah.
So if we have a look at the tranlocks view, so we can see here that we've got, so session 52 is the session that I'm in. So we have a key lock here. And what that means is that I've got a shared lock on anyone with the value of Buck on last name, but also any future rows with the value of Buck. So this is why it's a key lock rather than a row lock. I've also got, and remember IS, we talked about intent locks.
Yep.
So I've got an intent shared lock at the page level here. So page 281 in the first data file. I've also got an intent shared lock at the object level, so the table itself, and then I've got a shared lock in the database. So what this means is that anybody that wanted to do a table lock to delete all the rows, for example, wouldn't be able to, because you can't get an exclusive lock when there's an intent shared lock on there. So it's an indicator that further down this hierarchy there's a shared lock somewhere.
Right.
Make sense? So let's go to a different window and we'll do an update. So I'm just going to where we have this guy with a surname of Buck, I'm just going to update his title to be Doctor instead of Mr. I'm sure he'll be very pleased about that.
Change the database as well. You're not
Oh yeah.
anyway.
I think we're in T-SQL, aren't we? And I'm going to run that update now. So that update is now executing.
But it's not able to
still
complete because it's
executing.
waiting on the, yeah, okay.
Yeah, it's waiting on something. So if we have a look, if we have a look at these locks again, so we've now got a number of other locks going on here. So session 51 is this update that I'm trying to do. So we can see the locks that he's got here. And what's interesting here, so we have a look at this page 281. So it's the same page. So we've got intent exclusive. So he's looking to get an exclusive lock. Right. He has an update lock. So remember we talked about update locks. Is a way of, it's a lock that we need to read data before we're updating it. And that's compatible with a shared lock, so that's been granted. But what we're looking for here is a conversion to an exclusive lock, because we want to make a write, so we're doing an update.
Okay.
But we're only updating one row, it's still not working, so this is stuck.
Right.
Okay. So then we can have a look at DMV, and we'll talk about towards the end of this in terms of troubleshooting, called DMOS waiting tasks.
All right.
So within that, we can have a look at who is waiting for things. So basically we have a wait type here of a lock, LCK means lock, an exclusive lock. And what I can tell from this is that session ID 51, so we can see is executing, is waiting for a lock, an exclusive lock, and it's being blocked by session ID 52.
So if I'm troubleshooting blocking, then these DMVs are a great way to get to the bottom of, well, what's blocking what?
Yeah, exactly. Who's waiting for what? So then I can just, if I roll back this transaction, then this update has now
this
completed.
guy's finished, right.
So if I go back and have a look at my locks, we should see, so we've just got shared database locks because I'm using this database in both of these sessions.
Right.
So that's exactly what we were expecting to see. So the next part of this demo I wanted to have a look at was this concept of deadlocks that we mentioned, this deadly embrace. Yeah. So first of all, I'm going to set trace flag 1222 by using dbcc trace on. So this -1 means enable this trace flag for all sessions. So I could enable it just for this session, but force of habit, when I'm using trace flag to do it for everything. So I'm also going to set up Profiler. So Profiler is a tool that can be used to have a look at what SQL Server is doing when you execute code. And it's quite a heavyweight tool in itself, and is really beyond the scope of the sessions today. But what I wanted to show you in here was this deadlock graph that we'll produce. So I'm setting up this trace to be running, and when we experience a deadlock, we're going to capture some information about that.
Okay.
Okay, so in order to simulate this deadlock, what I'm going to do is set up a new window. There's a specific order of things that we need to do here. I'm going to begin a transaction in session 1 where I'm going to issue an update statement to update Buck to have title of courtesy as doctor. But because I'm not committing the transaction and I'm doing a change, it doesn't matter what isolation level I'm in here, because I still need an exclusive lock to do this. Okay. And I'm not going to drop that exclusive lock until I determine whether to commit it or roll it back.
So it's updated that row, but we haven't finished the transaction, so it's still going to hold on.
So it's still holding the lock, yeah. Okay. So then switching over to session 2, I'm going to do the same thing for somebody called King.
Okay.
So I do exactly the same thing. Make sure that's working. So if we flicked back and had a look at the locks that were held open, we can see that we have a number of exclusive locks that have been granted against these keys, and they're held because we haven't told SQL Server whether or not to commit them.
So I've got one held by session 51, one held by session 52, and because they're at the key level, we're actually down at those any row with that last name of Buck or King.
Yes, yeah, exactly. So now what I'm going to do is to try and do the same update in session 1 as I'm currently running in session 2.
So you're going to try and access the row that is being updated by the other session.
And this won't work because the other row is already doing this.
Okay.
The other session is already doing this. So that's going to stick there.
So it doesn't fail as such, it's just waiting for the lock.
Yeah, exactly. So it's waiting for the lock. Now if I switch over, and in session 2 I'm going to do the same thing as the first statement in session 1.
Okay.
So what I'm creating here is I'm going to update Buck, I'm going to update King, I'm going to update Buck, I'm going to update King. So they're both doing the same thing, just the opposite way around.
Right.
So they're going to be dependent on resources that each other holds locks on.
Okay.
So if I execute this now, it succeeded.
So that one didn't get blocked.
So this one succeeded because if we switch back here, we find that this one was chosen as a deadlock victim.
Right.
So SQL Server has automatically detected a deadlock situation and it's chosen a victim and rolled back the change.
Right. Okay.
Okay. Now if we switch over to, we start a new query and we have a look in the error log. Excuse my typing. can have a look at the bottom of the error log here. What you'll find is that we now have this deadlock information. Because of that trace flag 1222, we now have the deadlock information, which gives us the processes involved in the deadlock itself. So we can see that the deadlock victim was running this command.
I get pretty detailed information about what was going on in this deadlock.
Unfortunately, it's not very easy to consume because it is so detailed.
Yeah.
But it's one of those things that, because it captures so much detail, you're talking about the update locks, exclusive locks, so you can work out exactly what's happening. But a nicer way to view this information is what we've captured in Profiler.
Oh, okay. Pretty pictures, look at that.
Yeah, so within Profiler, we've captured this deadlock graph event of exactly the same thing. And we can see that we have session ID 52 on my left there, and session ID 51 on the right. And we can see the key locks based on the values that we were updating, and we can see the order in which we had update locks here. And we can see the blue cross. If we hover across, we can see that this is the statement that was chosen as the deadlock victim, which means this is the one that succeeded.
Oh, so that's pretty useful troubleshooting information. I guess that's easier to digest than what's in the log file.
Exactly. It's the intention is that it's much quicker, but you also need to bear in mind that Profiler is a client. It's called a client-side tracing, so it's quite a heavyweight tool, albeit not for this.
And I wouldn't want it running all the time just in case.
Yeah, exactly. It's an interactive desktop application, so you wouldn't leave it running there.
All right, great, fantastic. All right, so that's pretty much covered everything we want to cover about transactions and also isolation levels and locking, which are all kind of related to one another.
Yeah.
Transactions, we talked about the idea of implicit transactions. So every statement that modifies data is implicitly a transaction. But if we want to have multiple statements that are executed as a single unit that either all succeeds or fails, what we tend to call an atomic. People talk about ACID. Transactions where it's atomic, consistent, isolated, and durable. So it's then stored on the disk. So if you want to have a transaction that is that atomic unit of work that's all done and then stored, then you have to explicitly create a transaction with begin transaction, commit, and if you find an error, roll back.
Yeah.
And that then made us think about, that's great if I've got one person using the application, but if I've got multiple users at the same time, I want to use isolation levels to determine what can I read that may be in the process of being modified by a transaction. And it's a question of choosing the appropriate isolation level depending on which of those types of anomalies your application can deal with. Can I live with the fact that I read this data, but by the time I do something with it, another transaction may have modified it? Then we talked about locking and how the different types of locks, those shared locks for reading, the exclusive locks for updating, and the other types of locks, update and intent locks that we would use. And finally, how to troubleshoot locking problems, the fact that we have locks that block other processes, and in that deadlock situation where you have this kind of, after you, no after you, no after you type thing, where ultimately two processes are blocking one another, one of them is selected as the victim. And I guess the learning from that is, how do you troubleshoot that? And we can set those trace flags on. And also, how do you deal with that in an application? And fundamentally, it comes down to tracking for that deadlock victim error and retrying or whatever you need to do.
Exactly, yeah.
All right, so I hope you've enjoyed the session on transactions. Again, lots for you to get your teeth in here. If you are preparing for the exam, I do suggest that you read up on the different isolation levels and when they're appropriate, the types of anomalies that are permitted under each of those isolation levels, because that's a really important part of understanding which isolation levels that you need to choose. And please, once you've consolidated that information in your mind and you're happy and you're ready to go on, join us again for the next module where we'll look at some of the in-memory capabilities in SQL Server 2014. Well, hi and welcome back to Module 5 of this course on implementing databases with Microsoft SQL Server. We've covered a lot of ground up to this point. It's been a fairly long day for both of us so far. we've covered tables, we've covered indexes, we've talked about stored procedures and functions, and we've talked about transactions and isolation levels and locking and all of that good stuff. We're going to switch gears a little bit in this module and talk about some of the in-memory capabilities that have arrived in SQL Server 2014. Now, for those of you who are preparing for the exam was originally based on SQL Server 2012, and so of course didn't cover any of the new technologies, but it has been updated and revised with some additional objectives and additional questions that cover the 2014 additions to the product. And most of those changes in 2014 relate to the in-memory capabilities. So if you are going to be sitting the exam, then you do need to have an awareness of these 2014 specific technologies. So that's why we're going to cover them. Christian, do you want to tell us what we're going to look at in this module then?
Sure, thanks, Graeme. So first of all, we're looking at the in-memory features that are predominantly new for SQL Server 2014, but I'll talk about the specifics of that shortly. So the first feature we're going to have a look at is the buffer pool extension, or BPE. Then we're going to talk about column store indexes, which were introduced in SQL Server 2012, but we've had some changes and enhancements in SQL Server 2014, so we'll talk about those differences there. And then finally, we'll finish off by talking about in-memory OLTP, which is a brand new kind of headline feature for SQL Server 2014.
All right, fantastic. So let's start with the buffer pool extension then. Tell us
Great.
about that.
So the buffer pool extension, so the idea behind the buffer pool extension is that it enables you to extend SQL Server's cache to non-volatile storage, and what we mean by that predominantly is very fast storage. So solid state storage is really this kind of target, and you can think of it like a Windows paging file, if you're familiar with how that works,
okay,
but for SQL Server. So what we're looking at is clean pages, so committed data that sat in SQL Server's data cache will be paged out to this buffer pool extension that isn't as fast as RAM, but is faster than the traditional spinning disks that you might use. So it's really easy to set up, and we'll see that in a demo, but a couple of interesting scenarios for this. So the first thing to mention actually is that it's a feature that's available in SQL Server Standard Edition. And the first scenario that I kind of think about for this is around virtual machine density. So if you think you have a really large host, a Hyper-V host with, let's say 256 gig of RAM, and you need to host some large SQL servers on that host. Let's say you want 4 64 gig SQL servers on there. So that's fine, and you can give each one 64 gig. But if you use this buffer pool extension, you can really extend the usage of that and maybe give, each one 32 gig, but a buffer pool extension of 128 gig, so that you can provide each one with a lot more kind of usable buffer pool space. So the idea is that you could get more on a physical box than you could if you didn't use this type of technology.
So you're substituting your actual RAM in the sense of memory chips in the server for fast storage, where if we went to a traditional kind of mechanical disk, there's a significant performance difference in reading and writing data between RAM and disk, whereas if we go to a solid state disk, then it's somewhere in the middle. It's nearer to the RAM level than the mechanical level, so it's going to be quicker
true.
to
and it's certainly true that RAM is relatively cheap these days, but when we're looking at consolidating and virtualization, everything has a cost, and the more we can sweat these assets, if you like, the more kind of options that we have around kind of configuration and getting the best out of things.
I guess it's worth pointing out, I probably should have said this up at the top of the slide. This module is about in-memory technologies. This isn't specifically an example of in-memory technology. If anything, it's almost the opposite of that, but what it is doing is kind of addressing the importance of how we manage memory and how we manage data that is perhaps temporary rather than volatile, rather than permanently persistent to disk. And in this case, we're talking about something that SQL Server does anyway. It does a pretty good job of managing the cache, so that data that's accessed frequently is held in RAM. What we're doing is just being smart about extending that out to free up RAM for other processes, or as you say, if we're consolidating multiple servers on the same physical box, but still getting the performance benefits of caching by using fast storage to take the place of the RAM.
Yeah, exactly. And another scenario that I've really kind of considered for this, and that we've used with a few customers actually, is around public cloud virtual machine density. So you can get Microsoft Azure virtual machines with SSD storage presented. Now, the bigger the virtual machine, the more RAM, the more expensive it is, as with any kind of public cloud provider. Now, you could get a relatively small virtual machine with, say, I don't know, 8 gig, 16 gig of RAM with standard edition SQL Server. Standard edition has a limit of 128 gig of RAM, but you could then extend that onto the SSD provided with the VM, and really get this massive buffer pool. So you could extend that by 128 gig, 256 gig. You know, the idea is that you'd have a VM with 64 gig, and then you have a buffer pool extension of 256 gig. So you're enabling the product to do more with those resources without having to get a virtual machine that's 5 times bigger and upgrade to Enterprise Edition as well. So it gives you a lot more kind of configuration options to be creative with the solution.
So frequently accessed data that traditionally you would cache in RAM in order to get to it quickly. If you don't want to, pay for that amount of RAM that you would have in a public cloud hosted server, you can move that to fast storage in effect, and get a lot of the same benefit from caching it, but without paying the cost of having to have that RAM.
It's not going to be as effective as having all of it in RAM.
Sure.
But standard edition of SQL Server is limited to 128 gig of RAM, and this is a way for you to provide 256 gig of RAM, albeit a level 1 and a level 2 style RAM. But that may suit the needs of your application and give you a bit more kind of flexibility around that.
No, very nice. So let's take a look at just how easy it is to set that up.
So it's really, really simple to configure. So all I'm going to do is alter server configuration. I'm going to set the buffer pool extension to on, and I'm going to specify the file that I want to use for my buffer pool extension. So in this case, I'm going to create a 10 gig file, and SQL Server is automatically going to use that as an overflow for RAM. So let's just enable that.
And in this example, you've done that in the temp folder on C. I mean, obviously, just for the demo that works. In reality, we'd do this to perhaps a dedicated, in fact, probably a dedicated SSD device for this.
So the ideal scenario for this is that you would have very, very fast solid-state storage, and maybe even storage that plugs directly into the motherboard, so you're not going through the disk subsystem. That's really where you're going to get the best performance out of this. But the idea is you would put it on the best storage that you have, or the fastest storage that you have available.
Okay, great.
But yeah, obviously I'm running on my laptop, so I've only got a C drive. So now that's enabled, and we can actually have a look in the buffer pool extension configuration to see the details. So we can see that it's enabled and it's been set to 10 gig in size.
Okay.
We can also have a look at DMOS buffer descriptors. Now, this DMV is going to return 1 row for every page that is held in cache, so this data cache.
Okay. Regardless of whether that's RAM cache or...
Exactly.
Okay.
So, and then what we see from here, so we've got 1 row for every page in cache, and we now have this new column in 2014 is in buffer pool extension.
Okay.
So we can see when we're writing queries to analyze the configuration of the server, we've got the amount of data pages here, which databases they're from, and file IDs. So we could write quite complicated queries to really kind of pull out how much cache a particular database has in RAM, how much of that is being moved to the buffer pool extension. But the whole aim behind this concept is that you would enable it, and SQL Server will just use it in the background if it thinks it would benefit from it. So you don't need to do any more configuration than that.
Okay, yeah, fantastic, sounds good.
and switching it off is as simple as buffer pull extension off. And there we go.
It's off.
Yeah. So it's very straightforward. It's easy to switch on, easy to switch off. If the drive that it's running on runs out of space or are there any problems there, it will automatically turn itself off. So it's a very easy configuration to set up and just maintain and run in the background.
Right, yeah, I was going to ask you what happens if the drive gets pulled and the system detects that that's happening.
Yeah, because the only pages that will be moved to the buffer pull extension are what we call clean pages. So these are committed pages that haven't changed, whereas a dirty page is something that would be in main RAM that maybe we've changed in RAM, but that hasn't made its way down to disk yet. So we're only going to move clean pages out to the buffer pull extension. So if we lost that disk, we've got no data loss at all. We just dropped stuff from cache.
We're not losing any transactions by doing that.
Exactly.
All we've done is lose whatever was in cache, and the next time it gets queried, it'll be brought into cache.
Exactly.
Okay, great. Well, let's go back to the slides. All right, so that's the buffer pool extension. The other thing you mentioned right at the beginning was column store indexes, and I know these were around in 2012 and they've been enhanced in 2014. So tell us a little bit about those.
Yeah, so fundamentally, a column store index it's a different way of SQL Server storing the data in a table effectively. So what we have here on the left is a traditional row store. We've got two boxes there representing two different pages, and we've got 4 rows on each page there. Just get my screen together. And on the right hand side we have a column store index where it's been stored in a completely different way. So for the row store, on all of the columns for every row are stored within a single page. So if we take this example of data page 1000 on the left there, I've got 4 rows and all of the columns for those rows.
So a row can't span multiple data pages in that scenario, right?
Yeah. And then we've got another data page, and then we've got another 4 rows there. So, and that's the traditional way that SQL Server works and stores pages. But in this kind of data warehousing scenario, so we've got large scale reporting and large tables, so we've denormalize the table construct, and we tend to have very wide tables. When we're doing reporting off those tables, we tend to report on really a subset of the columns in the table. So we're not returning all of the columns, we're returning a subset. And if we're returning a subset of columns, row store isn't the most efficient way of storing those rows. So this is where column store comes in. So the diagram we have on the right hand side, we've got 3 pages there, but each page only contains data for a single column.
Right.
So they're all 8K pages. So, and if you think how many, the number of rows that you can store on a page will depend on what columns you have and the data types, because that influences the size of a row.
Sure.
And it's all got to fit within 8K. But whereas on a column store, if you take a single column, you can store many, many more rows for that one column on a single page than you could if you had all of the columns. And this is the first principle behind this column store technology, because if we're reporting off a subset of columns, in this example, if I wanted to find all of the order dates, or I'm doing a calculation on the order dates or whatever, if I'm reading a single 8K page there, I can read 4 times as many values than I could as if I was reading order dates from a traditional thing. So I'd have to do 2 8K reads instead of 1 8K read. So this is the first area where we're making a lot of savings in reading lots of data at once.
So that's the first area. I guess the other thing here is compression. We know that
Exactly.
column store takes advantage of the same technologies that we use in things like Power Pivot, which is a technology for Excel, where we're able to store huge amounts of data in memory by using in-memory compression. So how does that play into this story?
So the compression, so as well as storing column level data, we're also going to compress the data as well. So that means we're saving in 2 areas there. We've got more a lot more of one single kind of one single column on a single page, and it's compressed. So the amount of the volume of data we can read from a single 8K page is a lot more than we could read in a traditional row store model.
Sure.
So it's all about the speed of reading, and the idea is that you can read so much that you could do aggregations on the data on the fly instead of having to do these pre-calculations.
Oh, nice. Okay. So let's look at some scenarios for where we might want to use this. Clearly, if this was a panacea, we would just change the way that SQL Server stores data all the time. So there are some scenarios where this is more appropriate than others. Let's talk about some of those.
So it's really most suitable for, although as a technology it will work, it's really designed for data warehouse scenarios. So we're looking at star or snowflake schemas. So for those of you that have work in the BI world or have done the data warehousing exams will be familiar with these terms. Tables that have a large number of rows. So if you don't have very many rows, you're not likely to gain from the fact that we've got an enormous density of rows per page.
Sure.
And data that responds well to compression. If you've got a table full of GUIDs, it's not going to compress very well.
No.
So we're looking at lots of repeatable data. Text data is really going to compress really well and is really an ideal candidate for a column store.
It's worth thinking about how compression works in many different ways, but it's worth thinking about the idea that in a data warehouse scenario like we're talking about here, where you've got a star or a snowflake schema, the fact that you've denormalized the data means there's duplication. And duplication is a great friend if you want to compress, because instead of storing the same value 100 times, you can store it once and say, the next 100 rows store the same value as this one. So you can compress very, very much that way. All right, well, let's look at different types of column store index. And then people who are familiar with SQL Server 2012 but not 2014 might wonder what we're talking about. So let's talk a little bit about that.
So a custom column store index is brand new for SQL Server 2014 and is a much lauded feature. When column store indexes came out for 2012, they were fantastic, but one of the limitations was they were read-only. So the fact that we've got this clustered column store index in 2014, where we can create this index and read and write to it, is a real boost in the applicability of this technology to far more wide-ranging scenarios.
So yeah, absolutely. When you create we talked earlier on in one of the previous modules about clustered and non-clustered indexes, and
we did,
roughly speaking, the same sort of rules apply here. You can have one clustered column store index. As it happens, if you have a column clustered store, a clustered column store index, it can be the only index on the table. You can't have any additional indexes. Because it must include all of the columns in the table. So effectively you turn that table into a table that's stored in this columnar format, and that cluster effectively defines the table.
Exactly.
So that's our clustered column store, and as you say, that's updatable. We've still got the non-clustered variant from the previous version. So.
Yeah, exactly. So non-clustered column store indexes was the feature that was enabled in SQL Server 2012, and we still have that as an option there, in the fact that we could define a column store index as a subset of columns in the table. We can combine it with other indexes as well, but one of the limitations, the big one, is the fact that it makes the table read-only. So the way that we would have got around that in SQL Server 2012 is that you'd have nightly table loads, and then you'd create the clustered index, non-clustered column store index, and then you would use that for read workloads during the day.
And there are I don't want to give the impression that, hey, you should throw away all your non-clustered ones and use clustered ones because those are updatable. In that data warehousing environment that we're talking about, actually your fact tables tend not to be updated very often anyway. They tend to be read-mostly databases, I guess. And even when you are updating them, if you've got a non-clustered index, particularly if it's, let's say, a partitioned table, which is not uncommon in a data warehouse, you can create the non-clustered column store index on the table. You can create a table with a matching non-clustered index, and you can switch the partitions. So you could actually, load the new data that you want to add to your fact table, create a non-clustered column store index on that which will be fairly quick because it's only the new rows that you're adding on a daily load, let's say, and then switch that partition into an empty partition in the fact table, and you're able to update the table in that technique as well. So there's, it's not it's the end of the world, it makes the table read only. There are techniques you can use to make effective use of these things. But certainly the clustered column store index, where the table is updatable on a day-to-day basis, makes it easier to do those kind of ad hoc inserts and updates and so forth.
Yeah, absolutely.
That's all in this episode. I hope this tutorial was helpful. In the next episode, we will cover the remaining portion of implementing in-memory objects. Is your mind ringing with questions, queries, or doubts? Do you wish to learn more? Then visit our website www.millionlights.org and post your questions on our forums. We will be really happy to clear all your doubts. If you missed anything and want to rewatch it, you can download it from our website or can watch online as well. You can also participate in our webinars, discussion with the subject expert, as well as get a Microsoft certification on various courses through our website. You can also find us on Facebook by the name Millionlights and also on Twitter. For more such interesting tutorials on coding, app development, programming, and building rich UIs, keep watching Microsoft Hour of Code, brought to you by Millionlights. Thank you.